and in particular, Misha and Harold for organizing such a wonderful conference. I feel really fortunate to be here, and it's a real pleasure. The title is rather long and may seem a bit obscure, so it'll become clear, I hope, as time goes on. Let me first get this straight here. I apologize also for the old technology. Which one? So this right. So how did you scroll? Just this? Okay, good. Okay. So I want to start with minimal surfaces in the three-sphere, and then we'll also consider minimal surfaces in other constant curvature geometries. So this, of course, there's immersions and embeddings, but we're going to focus essentially on things which are embeddings, minimal surfaces which are embedded, or somewhat related to embedded minimal surfaces. So this subject really began with the groundbreaking paper of Blaine Lawson in the late 60s, who proved the existence or constructed examples of minimal surfaces of an arbitrary genus embedded inside the three-sphere. Since then, there's been a number of developments and further constructions, and so here's a list of just a few examples of work by Karsha, Pinkel, Sterling, Cho, Sarre, and the work of Capelius and Yang that Frank Picard talked about yesterday. This is a short list. I'm sure there's much more work that's been done in this area. So this gives you the existence of such minimal embeddings, and the subject I'm going to talk about is more about the space of all possible such embeddings, not focusing on the existence of one or the other, but the structure of all possible ones. One of the foundational results about that's going to be important for this talk is another result of Lawson, that a minimal embedding inside the three-sphere is unknotted. So this means that the complement, if you remove the embedded minimal surface from the three-sphere, what you have left is two components, and both of those components are handlebodies. So a minimal surface gives you a Heegard splitting of the three-sphere. So these are embedded minimal surfaces. I want to consider somewhat more general surfaces than embedded, namely Alexandrov immersed minimal surfaces inside the three-sphere. So these are given by, you have a surface sigma, a surface sigma, which is the boundary of a three-manifold, and you have an immersion of the boundary into the three-sphere, and Alexandrov immersed means that immersion extends to an immersion of the full three-manifold into the three-sphere. Given such a setup, on the three-manifold M, then you have a natural constant curvature metric, a constant curvature plus one metric, namely just the pullback of the metric on the sphere. So, of course, if the surface is embedded, then it's automatically Alexandrov immersed. This M here is just either one of these two components. So an embedded minimal two-sphere gives you two Alexandrov immersions on each component. So this will give you then a three-manifold with boundary, and the boundary then is a minimal surface, so a minimal boundary, h equals 0. Now again, Lawson's result applies in this more general setting, and again, his result shows that the topology of the three-manifold, which has this minimal surface boundary, is not arbitrary. In fact, it must also be a handlebody, just in the case of an embedding inside of a three-sphere. So the structure of the three-manifold is restricted then, in this case, to be a handlebody. If in the case of an Alexandrov immersion, in case you have an immersion inside the three-sphere, this is the case where the holonomy is trivial. You can view the three-manifold M as its metric of constant curvature 1 as an abstract three-manifold, and it has trivial holonomy in the sense of Thurston, for instance. Since M is a handlebody, the fundamental group has this very simple description of a free group on G generators. The generators are, for a surface of genus 3, the generators are just these 3 loops going around the three holes here. Given that, you might as well go one step further and consider then just general 3 manifolds. Not necessarily Alexandrov immersed, but just general 3 manifolds with abstract metrics of constant curvature +1 on them, which have mean curvature 0 at the boundary. And again, Lawson's result applies in this setting and tells you that the topology of M is controlled. It has to be a handlebody. But now, instead of having an immersion of M inside the 3 sphere, you may not have an immersion of M inside the 3 sphere. Instead, you may have non-trivial holonomy. So this is measured by the holonomy map, which gives you a representation of the fundamental group of M into the isometry group of the 3 sphere, which is SO4. So to this 3 manifold M, you have a naturally associated element in the representation variety or the character variety of M. So the space of homomorphisms from the fundamental group of M into SO4. Since the 3 manifold is a handlebody, this representation variety or character variety has a very, very simple form in this case. It's just the product of SO4, G times, modulo the adjoint action of SO4 on that product. So you have this nice, has a nice simple structure. Given this, you can more or less do exactly the same thing now for any constant curvature geometry, not necessarily positive or spherical. So in general, let's consider, in the general case, you no longer have Lawson's theorem that tells you the topology of M is restricted to be a handlebody. So instead, we're going to assume that. So assume now you have a 3 manifold with boundary, and assume that 3 manifold is topologically a handlebody. And just consider, abstractly if you like, the space of all constant curvature lambda metrics. So lambda is an arbitrary number, positive, 0, or negative, but fix it. We're not going to consider lambda varying. Just choose any lambda you like and consider the space of constant curvature metrics on that 3 manifold, which are moderately smooth up to the boundary. Cm alpha up to the boundary. Cm alpha is the Holder space. There's mild restrictions on M and alpha here. So this is the space of symmetric bilinear forms whose curvature is this constant lambda. We want to consider a moduli space, consider equivalence classes of metrics up to by isometry. There is an issue here which metrics you want to consider to be equivalent. The natural gauge group in this case is not all diffeomorphisms of the manifold, but diffeomorphisms which fix the boundary, so which are equal to the identity on the boundary. We'll consider somewhat different moduli spaces later on, but this is the one to start with. So these are diffeomorphisms which don't move the boundary around. They fix the boundary, but they can move around the metric in the interior. So what does an element in that space look like? Well, if you're varying the metric G, so if you're varying G inside this space, what is it you're doing geometrically? Well, there's 2 things you're doing. First of all, you can be moving the boundary of the manifold around inside the manifold. So imagine that you have a manifold with boundary, but it has a thickening. You can enlarge the manifold. You can enlarge the constant curvature geometry to a larger geometry. So then you have a boundary inside. Then you can move this boundary around inside this larger constant curvature space. That's one way of varying the metric G inside this space here. Another way is to vary the holonomy. As you vary the holonomy, the geometry of the metric G is going to change. This is a more global variation of the metric. And the general variation is the combination, an arbitrary combination of these 2. So again, if you have such a setup of M and boundary M and say lambda is positive, well, we'll see here in the picture, I guess. So the general setup then is you start with your 3 manifold M with constant curvature lambda. It does not itself immerse into a constant curvature geometry. What you have to do is pass the universal cover. The universal cover has a developing map So a developing map into the spherical geometry or a flat geometry or hyperbolic geometry, depending upon the choice of lambda. There's a developing map is an isometric immersion of the universal cover into one of these simply connected space forms. On the universal cover of M, the fundamental group acts by deck transformations isometrically, and the holonomy gives you a map from pi 1 of M to isometries of your constant curvature space. So the group generated by the image of rho is a group of isometries of the space form, and you can take the quotient of your space form by that group of isometries and consider the quotient. In general, this quotient could be a real mess. No reason to think it's going to be a nice manifold in general, but in some situations it will be. For instance, if lambda is less than 0, typically what will happen is that the image of rho will be a Schottky group. And then this pair M, boundary of M, will be a complete Schottky manifold. So the picture you should have associated here is that you have Schottky manifolds. These are hyperbolic 3 manifolds on a handlebody. They're complete hyperbolic 3 manifolds. The boundary at infinity, at conformal infinity, is a surface of genus G. But inside this complete hyperbolic 3 manifold, you may want to look for minimal surfaces. So in studying geometrically finite hyperbolic manifolds, the convex core, the smallest convex set, the convex core, the boundary of the convex core is an important surface in hyperbolic geometry. But one could also consider minimal surfaces inside Schottky manifolds. So this is one example of things that we're sort of looking at here. Similarly, if lambda is 0 in the flat case, it could be, it's not necessarily the case, but there will be examples where your holonomy is, in fact, the image of your holonomy just generates a group Z3, a lattice, Z3 inside R3, and so when you pass to the quotient, you get an immersion of M into a 3 torus, and the boundary of M is then a minimal, Alexandrov immersed minimal surface inside this flat 3 torus. So this is analogous to the sphere. You can have these generalizations of Alexandrov immersions in flat and also hyperbolic geometries. So that's the setting. So again, we're looking at this. To start off, we're going to look at this space here, this moduli space, the space of constant curvature metrics in the interior or in the bulk, which have some kind of boundary attached to them. The metric has a certain degree of smoothness up to the boundary. So given that piece of data, one thing you'd actually want to do is consider the boundary data. So to a given metric, you can consider the induced data you have on the boundary from that metric. The most natural and simplest thing you could do is given your metric G, just associate to it the induced metric at the boundary. This is, of course, Dirichlet data. I guess when I first looked at these things a number of years ago, it was a real shock to me, but being naive in some sense, I guess, that this boundary value problem, you think of constant curvature metrics, those satisfy a PDE, like the curvature gives you an equation, and the equation is like an Einstein equation, and it's kind of elliptic. It looks like Laplace's equations, and the simplest boundary data for Laplace's equations are Dirichlet data, and that gives you elliptic boundary data. But that's not the case here for metrics. For metrics, this Dirichlet data, although it's very natural geometrically, does not correspond to an elliptic or well-posed boundary value problem. We'll see more of this shortly. But so studying this map here is essentially the isometric immersion problem. So let's say let's say lambda is positive. Say lambda is +1. So we want to look at constant curvature +1 metrics. Say on a 3-ball, the boundary is a 2-sphere. You'd like to know if this map is surjective, for instance. If saying this map is surjective would be saying that given any metric on the 2-sphere, you can find an immersion of the 3-ball who's in R3. So that gives immersion of the 3-ball in R3. So that'll give you an immersion of the 2-sphere in R3 whose induced metric is gamma. This is the classical isometric immersion problem, which is notoriously difficult, and nobody has any really good ideas or program to try to attack this very classical problem. It's very interesting, but very, very hard. In particular, it's not elliptic. So instead, we're going to look at not that data, but this data. Pi h here is going to associate to a given metric g, not the metric on the boundary, but you, instead of looking at the full metric, drop 1 degree of freedom, drop one piece of the metric, and just look at the conformal class of the metric. You look at so then you're sort of losing 1 degree of freedom, namely the exact conformal factor. To counteract that or to balance that, add on the mean curvature of the boundary. So consider this combination. This does turn out to be an elliptic boundary value problem in a natural sense. It's on this moduli space. So when you divide this, take the space of all metrics, modulo this diffeomorphism group, equal identity on the boundary. This map here is Fredholm, so it has finite dimensional kernel and co-kernel, and its Fredholm index is 0. So, so this map has very nice local properties. The global property of this map is then somewhat of a different question, but locally everything is very nicely well behaved. Again, just notice that here, this moduli space, you're modding out by diffeomorphisms equal to the identity on the boundary. For such diffeomorphisms, those diffeomorphisms leave the metric invariant. So if you have a diffeomorphism equal to the identity on the boundary, of course, then the metric doesn't change. So the metric is invariant, so it passes to a, that's saying this map here is well defined. Similarly, the mean curvature doesn't change if you change the metric by diffeomorphism equal to the identity on the boundary. Now let's consider then, so anyway, this is an interesting map to study. We're going to now not study this in general, but look at certain special values or certain special range of this map. Namely, consider, so this C here is the same as the CM alpha boundary of M. Look at the space of all conformal classes, pointwise conformal classes of metrics, say CM alpha metrics on the boundary. And instead of looking at all possible values of H, mean curvature is just to restrict yourself to 0. So we're looking at minimal, H equals 0, we're looking at minimal surface boundaries. And look at the inverse image of that inside your moduli space of metrics. So that's some set M tilde. At the moment, all this is some set. I should have maybe mentioned this. I should have mentioned maybe this. This map is this space here is a Banach manifold. It's a smooth, infinite dimensional Banach manifold. It's not finite dimensional. It's smooth, infinite dimensional Banach manifold, as are these spaces here. And this is a smooth map of Banach manifolds. On the other hand, this guy here, as in terms of a definition, is just a set, the inverse image. So this set is a set of lambda metrics which have minimal boundary, H equals 0. Everything I'm saying here can be done just in exactly the same way for H equals constant. The whole process, all the results, everything I'm saying apply equally to H equals 0 or H equals constant. It doesn't matter. Okay, so this space M tilde now, it's invariant under the action of a larger diffeomorphism group, namely not only the diffeomorphisms which equal the identity on the boundary, but the diffeomorphisms of so yeah, this is somewhat notation here is a little bit off. The diff 0, this should be M. Diff 0 M is the diffeomorphisms of M into itself, which map the boundary into itself, which map the boundary to the boundary, so preserve the boundary, and which are isotopic to the identity on the boundary. And in the case your boundary is a torus, you have to also choose a base point and restrict diffeomorphisms, which are base point preserving diffeomorphisms for toral boundaries. So now that's a larger diffeomorphism group, but this space M tilde now is invariant under that group, and so you can divide everything, the action of this large diffeomorphism group on both sides, and consider then this quotient here. So this space script M is now the moduli space of constant curvature metrics with h equals 0 or h equals constant on boundary of M, where the metrics are now not parameterized, but they're allowed to vary by diffeomorphisms. So putting this together, then you obtain then an induced map M. So this big map pi here, pi h up here. When you restrict to h equals 0, look at the inverse image. Look at the induced map after dividing by this large diffeomorphism group. Then gives you a map pi or pi h from this set of constant curvature metrics with minimal boundary to the Teichmuller space. So here's sort of a very rough sketch of it. So you've got a surface, say, of genus 3, which is a handlebody. We're restricting ourselves to handlebodies. So you've got this bulk manifold in the interior. And on the boundary, you've got h equals 0. And you've also got some conformal class, and we want to study the behavior of this map from this set of these metrics here to the Teichmuller space. Okay, so here's the main result. So this map here, behavior is somewhat different in the case of higher genus and genus 1, which is maybe not too surprising. Suppose this genus is at least 2. If the genus is at least 2, then this space here is a smooth manifold, in fact. And moreover, its dimension of this manifold is, in fact, the same as the dimension of the Teichmuller space, namely 6G minus 6. And not just that, in fact, this map here is, pi is, in fact, it's a smooth map of manifolds, finite dimensional manifolds, and it's everywhere a local diffeomorphism. I should say that this space M here may have lots of components, just like in the case in the very beginning when you have embedded minimal surface inside the 3-sphere, so one of Lawson's surfaces, for instance, the complement of that gives you 2 components. So that gives you two 3 manifolds with boundary that give a minimal surface. You expect that will give you at least 2 components to this. 2 components of this space script M. It's likely this space script M can have lots and lots of different components. But regardless of which component, this map is always a local diffeomorphism. And all of these facts here are basically proved by showing that the kernel of the linearization of this map, the kernel of d pi, called k here, is always 0. In fact, the proof is really done by showing that h equals 0. This value it's a regular value of the big pi h. So when we go back up to where we came from, we started off with this map here, pi h. This is now the infinite dimensional setting. This guy here is a regular value. C cross 0 is a regular value of this map pi h. I conjecture also that this map pi is in fact not just a local diffeomorphism everywhere, but it's in fact a global diffeomorphism on each component. I forgot to add a line here. I would make this conjecture only in the case of lambda positive. If lambda's 0, it's sort of borderline. It may be true with lambda 0, but lambda negative it's much harder to say. So in the hyperbolic case, it's much. I really have no idea whether this map would be a global diffeomorphism or not. Showing this map as a global diffeomorphism would be tantamount to showing that the map pi itself is proper. This is the higher genus case. in the genus 1 case, the same proof, the same method of proof, the same ideas show that script M is still a smooth 2 manifold. For all the components of script M are 2 manifolds, but this fails in general. This is no longer true. So there's 2 cases. So you have a dichotomy. There's a dichotomy which, on each component of M, either you have everywhere in that component the kernel of linearization is trivial, so you have a local diffeomorphism everywhere. This case is characterized by the fact that this case can only happen when the boundary, which is topologically a torus, is in fact a Clifford torus. The boundary, the induced metric on the boundary is flat, the second fundamental form is parallel, and you have an isometric S1 cross S1 action. So this is a very rigid situation. This can happen only in very restricted situations. If that doesn't happen, then pi here is everywhere of rank 1. So the dimension of the kernel is not 0, but the dimension of the kernel is identically 1 everywhere on this moduli space script M. And geometrically, this is characterized by the fact that the boundary of M in this torus is a surface of revolution. You have a corresponding isometric S1 action. So these results give a different perspective, a different proof of recent work of Brendle on the solution of the Lawson conjecture for the fact that the Clifford torus is the only embedded minimal torus inside S3. There's a further proof of this result due recently to Laurent Hauswirth, who is here with Kilian and Schmidt. There's related work by both these authors, so Brendle and Hauswirth, Kilian, Schmidt, in the CMC case. And that was also handled by Andrews and Lee. So the analogous results to these hold for constant mean curvature boundaries as well, not just minimal. So, this is the main result I want to talk about, and so the second half of the talk is giving you some ideas of the proof of this result. Maybe before I get to the proof, this is more of an open question kind of issue. So we have this map pi from. So again, we're looking at handlebodies, constant curvature handlebodies, constant curvature matrix lambda with minimal boundary, and that's a smooth manifold. We get a map to Teichmuller space. These are equidimensional. There's also a natural map, the holonomy map, taking your constant curvature metric and reading off its holonomy. You'd like to say there's a natural map going here. At least locally there is. Locally you can invert this map and then go down here. And if this conjecture is true that you have a global diffeomorphism, then you could actually globally you could go back here and then back down here. So this gives you some kind of either local or global map from here to here. And it would be very interesting to understand this map better, to know it in more detail. All these spaces have the same dimension. There's a big difference between this space and this space, though. Teichmuller space, as we all know, the topology of Teichmuller space is very well understood. It's non-compact. It's a ball. It has dimension 6G minus 6. This representation variety, its topology changes, is quite different according to lambda. The simplest case is when lambda is positive. When lambda is positive, we can write down the formula for what this space is. We wrote it in an earlier slide, but the simplest grossest difference between this space and this space when lambda is positive is this space is compact. So when lambda is positive, you have SO4. SO4 is compact. A product of SO4s is compact divided by the adjoint action. That's compact. So this space is compact. This space is non-compact. So there's no way this map here can be anything like a diffeomorphism. The kernel of this map. So moreover, this space is not a smooth manifold. This is an algebraic variety, and it has Zariski tangent spaces, but it doesn't have tangent spaces in the sense of smooth geometry. But nevertheless, you can talk about the kernel linearization. And the kernel linearization of this map is, consists of Jacobi fields for the minimal surface, which are non-killing, non-trivial Jacobi fields. And it's, so there's this very interesting classical question for minimal surfaces, say in the 3-sphere. Say you have embedded minimal surfaces in the 3-sphere, are there situations where you have non-trivial Jacobi fields, or not? If you have an embedded minimal surface in the 3-sphere, does it always have no non-trivial Jacobi fields, or are there examples where there are non-trivial Jacobi fields? This is still unknown. It's a very interesting question. Very recently, this past summer, a paper appeared in the archive by 3 authors, Paolo Piccione and 2 others, showing that the analogous situation here, not for the 3-sphere, but for tori, if you look at Alexandrov embedded, or maybe they're, I forget exactly if they're embedded or Alexandrov embedded. I think they're embedded, actually. There are embedded minimal surfaces of genus 3 inside tori, flat 3 tori. So embedded minimal surfaces of genus 3 and flat 3 tori, which do have non-trivial, so non-killing Jacobi fields. So this was quite surprising to me, certainly. And so in the flat case of flat geometry, you can have these non-trivial Jacobi fields sitting in flat 3 tori. And for the 3-sphere, it's very interesting to know whether that's true or not. So this is more of an open question. Okay. So what are some of the ideas of the proof? So again, the basic issue is to study this kernel K. So we look at this map pi h. So that's this map. Going back to the Banach manifold setting, this map pi h here. So this is this nice smooth Banach manifold, and this is a nice smooth Fredholm map of Banach manifolds. And you want to study its kernel. Its kernel at the locus where h equals 0. So what does an element of that kernel look like? What does that kernel consist of? So an element in the kernel, kappa element in the kernel, consists of infinitesimal constant curvature deformations. So these are deformations of metrics which preserve constant curvature. So there's symmetric bilinear forms on the manifold. And because they preserve constant curvature in dimension, well, in any dimension, but constant curvature is very, very special. So a constant curvature deformation is very, very special kind of deformation. And all such are, in fact, just lead derivatives of the metric with respect to a vector field x, or twice times the delta star, the adjoint of the divergence of x. This formula holds globally. So kappa is globally represented in this fashion here. In the case in the case of trivial holonomy, in case your kappa is not changing the holonomy. If kappa is changing the holonomy, then this is not true globally, but it is true locally. So it's true up on the universal cover. On the universal cover, there will be a vector field x for which this is true. So these are exactly, these are actually elements in the tangent space to the space of metrics of constant curvature. So these are relatively simple looking objects. And what characterizes the kernel is that at the kappa is in the kernel of d pi h if at the boundary kappa t, so this is the restriction of kappa is a symmetric bilinear form on M, restricted to the boundary, and restrict the form to just a form on the boundary. If that form on the boundary is just a multiple of the metric, phi is a function, some functional multiple of the metric, this means it doesn't move the conformal class. The conformal class is fixed under variation in the direction of kappa. And when you vary the metric in the direction of kappa, you're not changing the mean curvature. The variation of the mean curvature in the direction of kappa is 0. Okay, so that's the data you have. That data is roughly half of the full Cauchy data, which is for an elliptic problem, that's always what you have. For elliptic boundary value problem, you always have half of the full Cauchy data. The full Cauchy data consists of the full variation of the induced metric on the boundary. So kappa t is the variation of the induced metric on the boundary surface, and a prime kappa t is the variation of the second fundamental form induced by kappa. So given a surface inside an ambient geometry, three-manifold geometry, you have the metric and you have the second fundamental form. We're varying the geometry by kappa, and so you can look at the variations of those of the first and second fundamental forms. The first part corresponds to Dirichlet, the second part corresponds to Neumann. So here we have a piece of Dirichlet data, and here we have a piece of Neumann data. But this is just a piece of each, not the whole thing. So the main approach, just to summarize, how the argument's going to go, is to show that an element kappa in this kernel here is going to in fact preserve the full Cauchy data and not just this piece of the Cauchy data. So show that kappa satisfies these conditions here implies that kappa in fact preserves the metric and the second fundamental form to first order at the boundary. Once you have that, then things are, then you're essentially done. If you can prove that, then unique continuation theorem. Here you have to use for this to carry through this unique continuation argument. You do need to know that all of the fundamental group is carried by the boundary. So you do need to know that something like the manifold is like a handlebody. Otherwise, yeah. Well. So anyway, the fact that M is a handlebody is being used in this unique continuation argument, and that shows that the Cauchy data vanishes at the boundary. In fact, the form itself has to be zero. So this is showing the kernel is then as zero. This is just a linearized version of a well-known fact that you all know about the fundamental theorem of surfaces and space forms. If you have a surface inside a space form of constant curvature lambda, then up to isometry, the surface is locally determined uniquely up to rigid motion, locally by the metric and the second fundamental form. This is just a linearized version of that. So here's a little warning that you have to be. Things are going to be somewhat tricky. Note that if you have conformal killing fields tangent to the boundary, and these are non-trivial conformal killing fields, namely that they're not killing vector fields, but they're non-trivial conformal killing vector fields tangent to the boundary, then these guys here generate non-zero elements in this kernel. So this kernel is going to be non-trivial whenever you have non-trivial conformal killing fields. I mean that's sort of obvious. Just if you have if kappa t, so kappa is just the lead order of the metric with respect to x, and if x is tangential at the boundary, so if x is a vector field which is tangent to the boundary at the boundary, then a conformal killing field is exactly an x for which this lead derivative here is a multiple of the metric. That's the definition of conformal killing field. So this condition is automatically satisfied for conformal killing fields. And if the vector field is tangent to the boundary, then of course it's not moving the boundary, so the boundary is staying minimal. So of course the mean curvature is staying zero. If you're just moving the boundary, just reparameterizing the boundary, just moving the boundary into itself. So it's trivial to see that conformal killing fields satisfy these conditions. So let's let this so-called strong kernel, just some word, I don't really know what to call it. Strong K is a set of kappa for which kappa t is a multiple of the metric. just like here. So this part here is the same, but instead of assuming this condition, assume the much stronger condition that the full second fundamental form vanishes at the boundary. The variation of the variation of the full second fundamental form is 0 at the boundary. So this is a much stronger condition than the condition of being in the kernel. So this guy here is certainly in the kernel, and in fact, conformal killing fields are in this strong kernel. So things are going to be different. So there's going to be a dichotomy between the situation where you have conformal killing fields in the boundary and where you don't. That points in the direction of there's going to be a difference between the situations where you have genus 1, tori. For tori, of course, you do have conformal killing fields, typically, not non-trivial ones. But for higher genus, you have no such. Okay. So there are 3 basic steps to the proof. By far the main step, where most of the hard work goes into, and is this first step, the main step, showing that if the strong kernel is 0, so if the variation at the boundary preserves the conformal class and the full second fundamental form, if that's 0, so if this strong kernel is 0, that implies that the kernel itself is 0. So if you have, this is not quite the same thing as saying, but it's roughly saying if you had no conformal killing fields, then in fact the kernel is 0. It's not quite that simple, but morally it's kind of in that direction. So if you have no strong kernel, if you have no elements which satisfy this much stronger condition, then the kernel is trivial, and that's what we want to prove. This argument here holds for arbitrary genus. The second step is to show that if the genus is at least 2, then the strong kernel is in fact 0. So if this was just conformal killing fields, this would be trivial. If the strong kernel was, if you knew for some other reasons that anything in K had to be, anything in strong K here had to be a conformal killing field, well, of course, on surfaces of higher genus, there aren't any conformal killing fields. But this requires some work, but it's not so hard. It does use the fact that the manifold is a handlebody. Well, it uses in particular the fact that the dimension of the representation variety is 6G minus 6. And step 3, in the case of genus 1, you prove that the strong kernel is in fact always equal to the kernel. So in general, there's an inclusion here, but in the case of genus 1, these are in fact the same. And you have this dichotomy that the dimension of this space is either 0 or 1. If it's 0, then all conformal killing fields are killing. So if the dimension of K, we know that conformal killing fields are in the kernel. If there's no kernel, there's no conformal killing fields. So in other words, all conformal killing fields are in fact killing vector fields. That corresponds to the Clifford-Torres case. If the dimension of K is 1, well, on a torus, you typically have 2 conformal killing fields. The translation vector fields on a torus are conformal killing vector fields. If you only have one non-trivial one, that means one is a non-trivial conformal killing field, and the other one is in fact a killing field. And if the other one's a killing field, that means you have an isometric S1 action. So that's, in a few words, that's a very rough sketch of the outline of the argument. I'm just going to focus on this main step here and give you some ideas of how some of the ingredients of the proof of this first step here. So the starting point, is to consider this classical functional. So this is the Einstein-Hilbert action with the Gibbons-Hawking-York boundary term. So, this is just the integral of the scalar curvature. We're not normalizing this in the sense that is often done by mathematicians to volume normalize it to make it scale invariant and so forth. We're not doing that. This is just the integral of the scalar curvature. Minus 2 lambda here. This is capital lambda. This is some number closely related to little lambda, as you'll see in a minute. So this is just this cosmological constant term, just some fixed background parameter corresponding to the choice of constant curvature you want. So this is in the bulk in M, and when you're dealing with a situation where you have a boundary as well, Gibbons and Hawking and independently York, back in the 70s and 80s, noticed that you have a much nicer behaved variational problem when you add on a boundary term like this, which is in dimension 3 is just twice the integral of the mean curvature of the boundary. When you do this, the reason for doing this is that you look at the first variational formula for this functional. So this is the derivative of this action, or the variation of this action, at a metric g in the direction h. This is an h here. Just do a little calculation. Goes back to Einstein. This is, or Hilbert. This is minus the integral over the bulk manifold of E paired with H. E is the Einstein tensor, given in this form here. So the reach curvature minus the scalar curvature over 2 plus G plus capital lambda times G. And then you have this boundary term here, minus tau HT. Tau is the so-called conjugate momentum. It's very natural geometric quantity. It's just the second fundamental form minus the mean curvature times the metric. This is not trace-free, by the way. So the trace of this is minus h, I guess. Yeah. So this is just saying the divergence. So instead, you might consider just looking at the reach curvature, but in many ways it's better to look at the Einstein tensor in this form here. One of the main reasons for that is being that the divergence of the Einstein tensor is 0. So this is the first variational formula. It's a very nice formula. If you didn't have this boundary term here, h, the boundary term here would be much messier. It wouldn't be so geometric. It wouldn't be nearly as nice. So this is the compensating term to make this variation term nice. What's much more important for us is the second variation. So it could be the second variation. Just do a computation. So the second variation of the action at a metric g. Now g is Einstein. So this formula only holds if g is Einstein. So you take the second variation around an Einstein metric and vary it in two independent directions, h and k. So these are infinitesimal variations. The bulk term is the variation of the Einstein tensor in the direction k paired with h. And then you have the variation of the conjugate momentum here in the direction k paired with h. Then you have a few extra terms like this. These are not so important. They're algebraic. There are no derivatives involved here. So these we could easily write the exact formula, but it's of no real importance. They're just algebraic terms. What's going to be important for us is that, of course, this is a nice smooth functional. We have the equality of second derivatives. So this is symmetric in h and k. And so using this formula and using the symmetry, one gets this little formula here. This formula is of basic importance for the argument. I call it duality lemma. Here's the setup. So let's deal with just the simple situation where our form kappa is globally represented in this form here, delta star x. So x is now global. So we're not looking at the case where there's holonomy, just trivial holonomy. Similar formula holds in the case that there is a non-trivial holonomy, but let's just deal with the simplest case first. So assume kappa has this form here, and kappa is in the kernel. So you're sort of looking at the holonomy trivial part of the kernel. The kernel can have a holonomy non-trivial part and a trivial part. Here's if kappa's in the kernel. This should be. So we're assuming here h equals 0 at the boundary. For this formula, all you need is this condition here. You don't actually need that that the variation of the mean curvature in the direction kappa is 0. But you need h equals 0 and kappa in this form here. Then you have this formula here. So this formula here follows easily using this symmetry operator in these conditions, just a computation. So, so we know for kappa in the kernel, we know this, so this is given to us. So we know a lot about the behavior of kappa at the boundary. We don't know much about the behavior of the second fundamental form at the boundary. So the full Cauchy data involves the kappa itself at the boundary, which is determined modulo a scalar here. So here's the one scalar unknown. But the second fundamental form is almost, the variation of the second fundamental form in the direction of kappa is almost completely unknown. So this formula here is telling you that tau prime kappa, this is almost the same as A prime kappa. There's a one-to-one correspondence between tau prime kappa and A prime kappa. You can determine, you can understand the form of A prime kappa or tau prime kappa by this formula. So this is what we want to, this is what term we want to understand. We want to understand how does tau prime kappa behave. And here it says, well, you have to understand how these terms here behave. So the analysis now shifts to understanding these two sides here. Again, I'm going to make a simplification. Here's the main issue. Yeah, okay. So the main issue, right, okay. So starting from this formula, what is it we're going to do? Well, we're going to show that, that for all choices of HT here, HT is Dirichlet data for H, and H prime T, that's a piece of the Neumann data. H prime is over here. So for all choices of H here and H prime here, you can find an extension of H from the boundary into the manifold, into the bulk manifold. Find an extension for which this term here is 0. This is the main issue, the main where all the work really lies. If you can do that, so for arbitrary HT and for arbitrary H prime H, you can always arrange, find an extension into the bulk for which this is 0. Well, then these guys here are independent. I mean, these were arbitrary choices. So HT can be anything, and H prime can be anything. So this could be 0, this could be 0, and this could be anything, and vice versa. This could be 0, and this could be anything. If you can do that, since this term here is 0, then it's obvious then that this formula then implies that phi itself has to be 0, and tau prime has to be 0. And if phi is 0 and tau prime is 0, that tells you that kappa at the boundary is 0, because kappa is phi times gamma. So if phi is 0, kappa is 0. If tau prime is 0, that's easy to see that implies that A prime is 0. So both these are 0, and so the Cauchy data are 0, and so by this unique continuation argument, the K itself is 0. Thanks. Okay, so let's look at a special case of this. A special case of this is when phi here is 0. So that's somewhat of a simplification, but still many of the essential ideas still come through in this special case. So let's just assume phi is 0 here. Then this formula here now simplifies to this, and the same problem. So we have the same problem as before, and we want to show that for any h on the boundary, this should be an ht here, you can find an extension for which this term here is 0. This guy, tau prime kappa, it's closely tied with Teichmuller spaces. It's a transverse traceless tensor, so it's naturally tangent to the Teichmuller space. It's trace-free because of this preservation of the mean curvature condition, and it's divergence-free as a consequence of the Gauss-Codazzi equations. And so that's telling the fact that this is the most important for us, the fact that it's trace-free. So again, we want to show that for any ht, this guy here is 0. That's the idea. Well, we know by the fact that this is trace. So this is sort of a schematic picture of the space of symmetric bilinear forms on the boundary. So we're looking at the boundary surface. We're looking at metrics. So HT is tangent to the metrics. So this is a tangent space to the metrics. You can look at pure trace. So H could be pure trace at some function times gamma, or H could be trace-free. So this is the horizontal part, the trace-free part. These are tangent to the conformal classes. So in this vertical or fiber direction, you know that this term here is 0. So this pairing here, when you pair this with H, if you pair it with some vertical fiber, it's automatically 0. We want to know it's 0 everywhere, but we get sort of for free from this condition here that it's 0 vertically. And so the issue is whether it's 0 horizontally or not. So the issue is then to show that for all choices of variations of conformal structure, so trace-free H's, there is an extension into the bulk with that given conformal variation on the boundary for which this is 0. Of course, this is trivial if there are no infinitesimal isometric deformations, but there's no reason to believe that this is the case. So I'm running out of time here. So to get started on this, in a real sense, you have to gauge things. So you start looking at bringing in tools from elliptic theory. So we're going to look at not the linearized Einstein equations, but the divergence gauged linearized Einstein equations. So this linearization plus this term here, this is now an elliptic operator, and this data here is elliptic boundary data for the elliptic operator. And let's look at S sub gamma here is the space of variations in the bulk such that at the boundary, these conditions are at the boundary, H is divergence free. It's pure trace variation of the boundary, and its the variation of the mean curvature in the direction of H is 0. The operator L gamma maps the space S gamma to this space. This is an elliptic self-adjoint operator, and so by general elliptic theory, you have a split. You have an orthogonal L2 orthogonal splitting like this into the image and the kernel. This target space here splits as the direct sum. This is a finite dimensional. K is finite dimensional. The same result holds. So here we had gamma here. This is like conformal classes, but there's no real need to restrict to conformal classes here. You can do exactly the same thing by taking the equivalence classes not with respect to the metric, but with respect to not with respect to the metric gamma, but with respect to an arbitrary metric sigma. So sigma here can be an arbitrary metric, and you're taking equivalence classes with respect to an arbitrary metric, not just the given metric gamma. Do exactly the same setup, and this is again still self-adjoint and elliptic boundary value problem, and so again you have a splitting like this. And I'm really out on my. So if for some sigma near gamma, K sigma is 0. So whenever you have a splitting like this, you have a canonically defined extension operator. This is a standard fact in PDE. You can extend along the kernel, and you can extend so that for any boundary data you have, the variation E prime H is in the kernel. This is standard linear PDE. So if it so happened that K sigma was 0 for some sigma near gamma, if this is 0, well then you're done. It's easy. But that may not be the case. Let me just head to near the last slide here. That may not be the case. So if K sigma is not 0 for all sigma near gamma, then you get this representation that this integral here we want to be 0. Well, E prime H, you can make it equal to some element in the kernel, K sigma paired with NX for some K sigma in the kernel, but this is a global quantity, and you don't, who knows what it is? It's some global, mysterious, complicated thing. You really can't say much about it. The idea here, and this is the special feature of metrics, this kind of argument doesn't work for other fields like scalar fields or gauge fields or things like this. It's really a special thing about metrics, that you can construct a different slice to the image. So instead of slicing along the kernel, so the kernel is a slice to the image, instead of using that kernel as a slice, you can construct an explicit slice replacing the kernel here, which has the same property. And it has and these elements in this slice here are a very simple natural form. So they're just given by this expression here in the bulk. So you can prove that that elements of this guy here do form a slice to the image of sigma for appropriate choices of sigma. And now, because this is explicit, you can just do this computation. So E prime of H is equal to Q sigma, and here's Q sigma. You just calculate this, evaluate this on NX, do a little computation, integration by parts, and so forth, and you end up with this formula. You look at this formula. Well, this is the variation of H in the direction of delta prime of X, but delta prime of X is in the kernel. Delta prime of X is kappa. It's in the kernel. So by assumption, this is 0. This is kappa t. We assumed phi equals 0. We assumed phi equals 0. So this was also 0, and this is just the trace. So this is 0. So all these terms here are 0. So they sum to 0. So this gives you the gives you what you required, what you needed. Okay, that's a very, very, very brief idea. Some of the arguments or some of the styles of argumentation that goes into the proof. Okay, thank you.